not just in 2 dimensions, but we're actually probing in the 3rd dimension of altitude or pressure here. Unfortunately, this isn't really an option for us in transiting exoplanets, because what we're really dealing with is this. This is a single frame of a photometric image of the TRAPPIST-1 system. So from starting with something that looks like this, you know, there are 7 planets in there. There's all kinds of information that we've been able to extract from these types of images. And so how are we going to do that? How are we going to get from something that's just you know, a star spread out over a handful of pixels and actually start to spatially resolve a planet around that star? Before I get back into the how, let me tell you a little bit about the why. What are our motivations for doing this? Well, right now we have all of these transmission spectra, okay, which I'll kind of go back into in a minute, but we have all of these spectra of all these different planets, and we see kind of all of these different results, this continuum from clear to cloudy and hazy that David Singh put together so succinctly in his 2016 paper. Now, given this sample that we see this diversity, we want to understand why. Why are some of these cloudy and why are some of these clear? What I'm showing in this right panel here is that there is a set of planets, for example, WASP-6, WASP-39, and HD 189-733b, that all occupy very similar space in this pressure temperature diagram here. So if we have this one-dimensional look at their atmospheres, if that's what we're assuming, is that we retrieve just a one-dimensional pressure temperature profile, meaning that we're just integrating over the entire hemisphere, we end up with these 3 planets that should, based on that assumption, have very similar atmospheres, yet the observations tell a very different story. Well, maybe what the issue is that we are just using that one pressure temperature profile. We are assuming this homogeneity across the entire hemisphere, whereas in fact, that's definitely not what's happening. I mean, we can just kind of naively say there's no reason to expect that the thermal distribution would be uniform across these types of planets. We're talking hot Jupiters here, right? We have these extreme extreme radiative forcing on at the substellar point, driving these huge temperature contrasts, which are going to then drive these jets transporting that heat, but it also with very short radiative timescales. And so there's no reason to think that we have some uniform structure here where we can just integrate over an entire hemisphere and then set our chemistry and our clouds based on that. What's really happening is we have all of these different pressure temperature profiles depending on which area of the planet that you're probing. And so, for example, in a single transit observation, you're probing both the east and the western limb. Well, those eastern and western limbs may have very, very different profiles. And so what you're actually seeing, what you're actually observing, is the 2 of them kind of combined together. Why this becomes an issue, this is something that a lot of people have been thinking about and trying to figure out observationally, how can we separate these 2? How can we take this into account? But really what I want to have you focus in on here is this middle panel here. This is a study done by Kat Feng in 2016, where she took a simulated transmission spectrum and fit it with both that single hemispherically average pressure temperature profile, but then also used a 2 temperature pressure profile retrieval at the same time. And you can see that if assuming that single, that 1D model, that single PT profile, she got a very, very tight constraint in this example, a very tight constraint on the methane abundance. But in fact, again, if we assume that that's not really the physical setup, that the physical setup is something much more well represented by a two profile fit, you can see that when you do that, your uncertainties really blow up, and your constraint just becomes an upper limit. You really do not constrain that methane abundance at all. So if we are using this 1D treatment, are we biasing our results when it comes to chemical compositions and retrievals? And so the evidence says that we are. The question is, how do we get information then? How do we actually probe these non-uniformities so that the assumptions that we make in this data interpretation step are physically motivated or observationally motivated? So to do this, the tools of the trade, the tools that I use to try to answer these questions were the Spitzer Space Telescope. Although I guess I can still say are, because there's a ton of data that's still sitting out there from Spitzer, just waiting to be unlocked and analyzed. So I think that the Spitzer Space Telescope is going to influence our understanding of these thermal distributions for still years to come, as more of these observations, more of the phase curves that Spitzer recently did start to come out. So we use a Spitzer Space Telescope, and we can use the Hubble Space Telescope to do transmission or eclipse spectroscopy. This allows us to look at these planets over a wide range of wavelengths, exploring very different a number of different molecular features, and of course exploring a wide range of pressure levels, so we can really start to explore different ranges of that PT profile. The geometries that we're going to use, so this is where transiting exoplanets really give us a great advantage. As I showed you earlier, the actual observation is just that handful of pixels of the star itself, and so how from that can we actually get some information? Well, transiting exoplanets give us this unique opportunity to extract all of this information about the planet. Of course, in transit, the planet passes in front of the star, and photometrically, that gives us essentially the size, the radius of the planet, because that dip in light as the planet passes in front of the star is going to be proportional to the ratio of the radius of the planet to the radius of the star squared. And then, of course, as the planet passes behind the star in secondary eclipse, what we're going to see there is another dimming of the overall flux, and this one is going to be proportional to the thermal flux of the planet to the flux of the star. Depending on what wavelength you are looking in, you may need to consider that you could be seeing a loss of reflected light as well. But I will kind of preface all of that by saying that for what I'm going to talk about today, the wavelengths and the planets that I'm talking about, is that reflected light is not a significant contributing factor. And so we're going to assume that all of the drop in flux that we see is loss of thermal emission from the planet. So how does this look observationally? Here's a little cartoon that'll show you the planet in orbit around the star. Here we're going to show I guess I'll just step back for 1 second. I forgot to mention the thermal phase curve. So if we look at this system during the entirety of the orbit, we will see a variation in the overall flux as we see the various phases of the planet. So each phase of the planet is going to have some different thermal emission, and we will see that variability. And so here it is as an example. Our planet's tidally locked, so it has the same face, same substellar point throughout its entire orbit. So it has a very hot day side and a very cold night side. So as we see the day side here, we're at the peak. We lose it in secondary eclipse. And then as we go through the orbit, coming back towards transit, we're starting to see more and more of the night side. So our overall thermal emission is going down until finally we go back into transit again. So these are kind of all three of those geometries, the transit, the eclipse, and the full orbit phase curve, that I'm going to focus on and to show how we're able to get this 3-dimensional and even 4-dimensional information out of those non-spatially resolved images. Just a quick note about signal strengths. I mentioned previously that that transit signal was proportional to the radius of the planet over the radius of the star. And so that for hot Jupiters many times is on the order of, say, 1%. If we're talking about the features themselves, the molecular features themselves, those are determined by the scale height of the atmosphere, and those are generally a couple of magnitudes less. And so we could be talking about hundreds of parts per million for the molecular features in hot Jupiter atmospheres. And then, of course, the eclipse depth, secondary eclipse, this is scaled by the flux of the planet to the flux of the star. And again, it's usually on the order of 0.1% to even hundreds of parts per million itself. So orders of magnitude less in amplitude for the secondary eclipse than the transit. And then the amplitude of the phase curve, the amplitude of that kind of sinusoidal signal is constrained by the eclipse depth itself. So it will be of the same magnitude, same order of magnitude as the eclipse depth or less. For a very stark day-night temperature contrast, the phase curve amplitude will be similar to the eclipse depth. For a planet that has a well redistributed thermal profile, and that the day side and the night side are essentially the same temperature, that phase curve amplitude would go towards 0. So let's kind of go, continuing on with this idea of the tools of the trade. Just want to take a quick look at transmission spectroscopy, since that's what I showed you initially, and I said, these are the kind of observations that we're trying to inform. So this is an example, HST, wide field gamma 3 transit, and so the fuzzy looking box on the left, that is what the image looks like that we are provided from the instrument. That is the spectrum on the detector. And so from that, we sum everything up into a white light curve. As you see on the right-hand side, you can see that there's all kinds of funky systematics that come along with this type of observation. You have these kind of exponential ramps in each one of the orbits. So each one of those little segments where the observation starts and stops is an HST orbit. So about 90 minutes. HST orbits the Earth every 90 minutes. And so when an HST is occulted by the Earth, it cannot take any observations. And then as it comes back around, it points at your target and starts observing. But then you have all of this thermal settling and charge trapping going on that creates these hooks. Fortunately, there's been a lot of these done, and people have figured out how to model those systematics very well. And so once you do all those corrections, you get something that looks like the light curve at the bottom. That was the white light curve. Now you can split all of these up and just extract those light curves, one spectral bin at a time, and ultimately you end up with, I don't know, in this case, a dozen of these individual light curves. Each one of those is going to have its own unique transit depth, depending on whether or not there is molecular absorption at that particular wavelength. From those individual transit depths, this is how we construct our transmission spectrum. And so bumps that go up mean that the radius of the planet appears larger at those wavelengths, and that is indicative of some molecular absorption. In this example here from WASP-63b, an analysis that I led in 2017, 2018, we can see that at 1.4 microns, there's definitely a bump there that's indicative of water absorption. And then there's another bump out there at 1.55 microns that is potentially a HCN absorption, but not quite strong enough for it to be conclusive. But what I want to point out is that you see all of these little wiggles, all these different colors and these wiggle lines that come from all of these different models and retrievals. And so we're back to, how do you create, just based on this information, how do you create those models, and what assumptions do you make when you run those retrievals? You have to understand what you have to set some kind of temperature pressure profile in order to set the chemistry to run these types of, to do this types of interpretation. And so really what we want to get to is going back to informing these types of analysis. So one of the things I'll talk about a lot is secondary eclipse photometry with Spitzer. Okay, again, you're losing the thermal emission of the planet when it passes behind the star. On the top right there, what I'm showing you is molecular absorption or opacity for different molecules that are of interest as a function of wavelength. And that is a really crazy looking plot. There's a lot of things going on there. If you're not used to looking at these, I'm going to just try to simplify it for you. So that's a log scale on the left. And so if you look at about 3.6 microns, where I have a little blue box that says channel 1, that is Spitzer channel 1. That is where that broadband filter sits. And you can see that methane, that red line, that red model for methane, sticks up above all of the rest by a couple orders of magnitude in that band pass. And so we can know that we are really probing primarily methane when we look at Spitzer channel 1. And of course, in channel 2, you can see that we have kind of an equal contribution there between CO and CO2. So that's where we're going to get a lot of our information about our carbon-bearing species in comparison to something like wide field camera 3 on HST, which is down there at about 1.4 microns, where you can see that the blue water feature pops up above everything else by several orders of magnitude. So if we combine Spitzer observations with our HST observations, we get both the water feature to get oxygen-bearing molecules combined with CO and CO2 or methane. Why are these channels so advantageous for us when studying hot Jupiter atmospheres? Well, as I said, the signal strength of the secondary eclipse is going to be scaled by the ratio of the flux of the planet to the flux of the star. And so if you were to consider the star to be a black body, consider the planet to be a black body, the ratio of those two is maximized out here in these infrared wavelengths. And so we're actually sampling the peak of the energy density, the spectral energy density of the planet out here at these wavelengths and maximizing that ratio of the flux of the planet to the flux of the star. So we're ensuring that we're going to get large signals, as large of a signal as we can. I kind of showed you the HST systematics. I can't continue talking about Spitzer without showing you an example of the Spitzer systematics. There is a dependence on the overall flux in Spitzer photometric observations, depending on where on that central pixel the observation actually lies. And so what I'm showing on the left there is kind of a map of the central pixel, and there's a sweet spot right in the center that maximizes response. The color scale is what the detector response is if the image is centered at that particular point. And so at the sweet spot, it has maximal response, but it's also kind of plateaus there, and it's much more stable if you can stay in that region. Whereas if you start to drift away, you start to fall off very quickly, and you start to fall off by things like percents, by like several percent. That's a problem because, as I told you, our transits are only 8%, and our secondary eclipse depths are something like 0.1% or less. So we have this variability based on the instrument systematics that is of several percent when we're trying to extract a signal that is, an order of magnitude smaller. So on the right is a sample raw photometric extraction of an observation of a full orbit phase curve from Knudsen et al. 2012. And you can see the top two panels there, the X position and Y position. So this is kind of where on that pixel the stellar centroid was. And as you see that X position and Y position vary, you can look down at the bottom panel and see how the flux varies. So you see those short period, or those are, I think, about 40-minute, that sawtooth pattern that manifests in both the X and Y position, certainly goes straight through into the overall flux. And you can see how, again, that entire observation from start to finish varies by several percent. It goes from, about 1 in relative flux all the way down to 0.98. So you have a couple percent variation there. And from this, we need to reconstruct one of those nice, pretty sinusoidal looking phase curves. And so understanding these systematics is important and tricky. I'm not going to go into this slide very much, other than to say this is something that through my graduate career, I thought a lot about and spent a lot of time working on and testing multiple different methodologies on how to handle these systematics the best, comparing them, contrasting them, figuring out which types of observations are best treated by which types of systematic corrections. There are a bunch of them out there. And of course, everyone has their favorite that they think is absolutely the best. And so I spent a lot of time trying to figure out if there was one that's the best. And long story short, there's really not. There's some that aren't the best, but there's not any one that is the best. And it's best to have a number of them at your disposal so that you can treat each one of your observations with multiple methods and make sure that the result that you're getting is not dependent upon which systematics model you choose. So that's my little lecture there on how to handle Spitzer data. Okay, so Spitzer is one of the first to give us this kind of one-dimensional longitudinal information. So again, showing some example work by Heather Knudsen. This is one of the first phase curve observations that was done. And so here you're seeing the corrected Spitzer flux measurements on the left panels, zoomed in to see the transit, and then, or zoomed out to see the transit, and then kind of zoomed in just to really focus on that phase curve amplitude. And so dependent upon the flux at each one of those orbital phases, you can reconstruct this longitudinal map. So I want to point out that even though that globe in the top right shows variation as a function of latitude as well, really that's not accurate. That this is just a one-dimensional longitudinal probe. So the panel at the bottom that shows the relative brightness as a function of longitude is really what we're extracting from this. We can do this, we can do a phase curve. If we do it spectroscopically, we're going to have that longitudinal information, and we're also going to have the pressure dimension as well. So we're going to get 2 dimensions here if we can do a phase curve spectroscopically. And Kevin Stevenson did this in 2014 with WASP-79b, and made some cool graphics here that we can show and show you how the emission spectrum changes as a function of phase on the top left, and over on the top right, you see how that pressure temperature profile changes as a function of phase. So again, this goes back to where we started, that by doing this, we can see that this thermal profile definitely varies as a function of phase, and is probably something we need to be considering. Certainly once we start getting James Webb data, that is going to be much higher precision. This is something that we're going to have to take into account. Another way to get 2D information is eclipse mapping. Eclipse mapping was done twice in 2012. I say it was done twice because so far the only published eclipse maps were from, or the only observation, actually maybe it's 3 times now, but anyway, the only set of observations that have been eclipse mapped were done in 2012, and they were done by 2 different groups essentially at the same time. Here I'm showing a figure from one of those groups, which is Majot et al. 2012, that just illustrates how they constructed the 2-dimensional maps, and the balls on the bottom actually are representative of the result that they got. And essentially what they say is that during ingress and egress of the secondary eclipse, the slope of that line, the slope of ingress and egress, is going to be governed by the brightness distribution. So if the slope will be shallower as you traverse cooler regions and steeper as you traverse hotter regions, and that each one of those steps, ingress and egress, each kind of slice the planet at an angle by the limb of the star. And so if you combine the information that you get from ingress and egress, given that you have an appropriate impact parameter, those slicings will be somewhat orthogonal, and you can combine them to create this grid where you can reconstruct the thermal profile or the thermal distribution that you've just encountered. And so that's what they've done here. Is they took this, they basically take the slicings and ingress and create this map that you see in the bottom left, and egress on the bottom right, combine them together to get this distribution where you see a eastward shifted hotspot. Now I want to shift, so we've kind of laid out what the state is on probing thermal distributions. I want to talk about time now. And time is going to be really important as we move forward and start to try to get smaller and smaller signals. So why do we need to consider time? Well, if we think about Earth, for example, this is a IR thermal emission image of Earth, and you can see that due to our cloud cover, the observed emission in IR could change dramatically as a function of time. In comparison to something like Jupiter, where the large-scale structures are very, very constant, but you have small-scale variability that you have to consider and try to see how that's going to impact your broader observations. So as we study these planets and as we start to look at them over time, do we expect to see consistent eclipse depths? Do we expect that these thermal structures, these thermal distributions are going to be constant, or do we have to consider this variable climate on these planets? And so as I was preparing to this talk, I stumbled across this comment from Sarah Seeger. This was from a review paper back in 2010, saying that the variability in the hot Jupiter atmospheric data is relatively common at the 2 sigma level. While this would not be statistically significant in a particular case, it's highly suggestive in the aggregate because it occurs more frequently than is expected based on statistical error distributions. Possible mundane explanation is that observers have underestimated their statistical errors. Nevertheless, many observers are careful using error estimation, so we must consider this intriguing possibility that atmospheres of hot Jupiters are intrinsically variable to a significant degree. So this was something in 2010 that was definitely being thought about and was definitely something that was expected. In fact, there were models that would predict variability to as low as a % level in the overall eclipse depth, to variability in eclipse depths up to 20% based on certain models. And the idea was that these hot Jupiter atmospheres have very large temperature structures, So they have just a few bands. Unlike Jupiter that has many bands, these hot Jupiters are expected to have only a few bands. They're kind of their vortical structures are expected to be large, like something like the radius of the planet or half a radii of the planet type of large. So if these things migrated, these large structures migrated, that they could cause 20% level differences in the observed secondary eclipse depth. So, so we are going to do this study where we're going to look at this variability. Why? Well, we want to find a way to probe these smaller scale structures that we can't see. So, in similar to Jupiter's, where the large scale structure is maybe more constant, are there smaller scale structures that are going to manifest, that are going to be observable, that are going to cause small variations in what we see? We're also looking at studying processes that are happening deeper in the atmosphere than what our observations usually can access. And so if there's this kind of interplay between these wave processes and radiative processes deep in the atmosphere that other observations won't directly measure, are they causing changes that we will see based on this temporal variability? The other big thing here is the repeatability of the measurement and stacking multi-epoch observations. If you take 10 secondary eclipses and you want to stack them all together to improve precision, are you really comparing apples to apples? Do you expect each of those observations to be of the exact same thermal distribution so that you can combine them to build up precision to do things like eclipse mapping? Or are they just inherently different and you're just going to be smearing out, you're going to be combining very different images that are just going to kind of smear out and not really improve your precision at all? So the model predictions that we ran for our study said that we would expect variability for HD 189.733b and HD 209.458b are two targets, which are the canonical hot Jupiters, are the most well studied. They have more observations than any other exoplanet out there. And so they were the most well understood, the most well characterized, and gave us the best shot at really nailing down what was happening here. And so we predict something like a % variability for both of them. There had been previous work on this for HD 189. Eric Agel back in 2010 had constrained the variability to less than 2.7% with Spitzer 8 micron observations. So I mentioned already what our targets were, HD 209, HD 189. As I said, they were the most well-studied planets that we had. So there's a lot of observations that were already out there. You can see the programs listed in the bottom right in yellow. A Heather Knudsen program and the six series, a few from Mark Swain in the 7 series, a few from Kamen Todorov. And then given that there was already a lot of this information out there, Nicole Lewis wrote a program to add sufficient number to those already existing so that we would ultimately have the precision to potentially do eclipse mapping. So what this, aside from just giving us all of those extra eclipses to potentially eclipse map, this gave us this huge temporal baseline where we actually had a chance to start to probe this idea of temporal variability. Most exoplanets, most of these hot Jupiter atmospheres are observed once, and that's it, maybe twice. So there's no way to probe temporal variability because you just don't have a sufficient baseline. But given that we had these observations that were spread out by years, some of the observations were taken very close to each other, and some of them in groups, and so others spread out by years. It really gave us a really good baseline to look at both short-term and long-term effects. So here's just a sample of a secondary eclipse, just showing how the level of precision that we're able to get with a single eclipse, given that we're using all these different analysis methods and look at the residuals to see how well we do at reducing correlated noise effects and the like. So here's the results for our HD 189 from our variability study. And so you can see for 189, we ended up with, there was a few observations that ended up not being usable for HD 189, unfortunately, because they used a different observing strategy and ultimately didn't work for us. So we were left with 7 of I think the 10 eclipses that we wanted to have. And they're plotted here. The X scale is not to scale, so the dates are just labeled, but they're just evenly spaced there in this particular plot. And this is just to show you what the scatter and eclipse depth is in comparison to the uncertainty in the observation. And so I would say that the scatter and the eclipse depths in comparison to the uncertainty for each measurement doesn't suggest that there's any structure here, that there's any reason to think that there's variability affecting these. And so, and then for the paper, if you look at the paper, we did many more tests to show that there was no structure there. And so if we find that there's no structure there, given the amplitude of the scatter and our uncertainties, we can say that we can constrain the variable in this case to less than about 5%. And so again, the predicted variability is only about 1.5%. So We're not able to get down to the level where we would expect to see variability, but we are observationally reinforcing those models and putting a constraint there. In the case of HD 209, we didn't lose any observations. In fact, we had all 10 or 12 of them, depending on which channel you're looking at. And channel one with Spitzer is the channel that is much more strongly affected by systematics. And so you can see our eclipse depths for channel one. There's a lot of scatter there. And so really we're only able to constrain that variability down to something less than 10%. Channel two with Spitzer, however, is very, very reliable. And if you look at the scatter and the eclipse depths there, these things are consistent to within something like 25 ppm. Our variability in eclipse depth for HD 209 puts us at a constraint of less than 1.5%. So we are right at the doorstep of what the model predictions say we should get. So this is really interesting because it says that we're now putting a constraint on this that's right at the top of the model. So we have excluded all of these, a whole suite of models that predict greater eclipse depths. But again, because we are right at the threshold but haven't actually hit this variability yet, we can assume that we can stack all of these observations to build up precision, that this variability is not affecting our observations at the precision that we are capable of at this point. I want to draw your attention to the right-hand figures, which I haven't talked about yet, and that is the eclipse timing. What I've put here is the eclipse time, the observed minus expected. And you can see that essentially all of these eclipses have shown up about 2 to 2.5 minutes late. And that was intriguing because there's no reason to, there's not a explanation for that just solely based off of the ephemeris. If we consider things like, so if we consider, we would expect to, if you just calculate the eclipse timing based on a half a period away, you're not taking into account the travel time of the light across the planetary system. So you have to consider that in transit, the planet is 2 times the orbital separation closer to you than it is during eclipse. And so for these systems, that can be something like 30 seconds, maybe a minute, depending on which one, but it certainly isn't enough to explain 2.5 minutes. And again, you can see that this is very consistent, and this is a very consistent effect that we're observing. And a potential explanation was given in DeWitt et al. 2012, which is the other example of the eclipse mapping that I mentioned earlier, the 8-micron eclipse mapping of HD 189. And essentially what they've shown here is that if you assume just this uniformly bright disk as your model for your eclipse, you're going to have a tendency to have your observations show up a bit late, just because you're biasing it with your model. The black line there is the uniform disk model, whereas the red line includes this hotspot. And so because at the beginning of the observation, the star is occulting cooler regions, the slope is not nearly as great. And then once you hit that hotspot, it steepens very rapidly. And of course, the opposite happens during egress. And so if you look at that red model, you can see how if you were not taking that into account, your uniformly bright model would want to shift itself to the right and show up late. And so that's what we suspect is happening in these observations. And of course, then we also say, if you look at the bottom, you can say, well, if you are fixing the time and getting the timing right of your eclipse, but again, you don't model this thing as a non-uniformly bright disk, if you still use that black model, you're going to see these residuals. So if you see the deviation at the bottom, those red residuals there, you would expect to see something like that if you were in fact fitting fitting your eclipses with a uniform model when in fact it was not uniform. In fact, there was some non-uniform thermal distribution. So this just shows the calculated delays in eclipse time as a function of hotspot offset. So depending on where you put that hotspot is going to determine how far late your eclipse is going to show up when you're fitting it with that uniform model. And so HD209 is the blue line at the top, HD189 is the orange, that's a little lower. And given that our HD189 observations are showing up something like a minute and a half, there's a minute and a half left of undescribed or unaccounted for delay, we can say that that should correspond to something like a 37-degree offset. And similarly for 209, we can make a prediction on what the hotspot offset is just based on that delay in timing. So what we did then was we did the other test, which is we fixed the eclipse time to where we knew that it should be. And again, this is a very well-studied system, and so the timing of these eclipses, the orbital properties are very well known. And if we fix that eclipse time and still fit with just a uniform model, we in fact see exactly the structure in our residuals that are predicted by the model from DeWitt 2012. So all of this tells us, this is all evidence that we are actually observing something that has non-uniform thermal distributions. There's been evidence for this non-uniformity in previous observations for these particular targets. There's a 4.5 micron full orbit phase curve of Spitzer by Zellum and Lewis et al. In 2014. And what you're seeing here is that the secondary eclipse does not correspond with the peak of thermal emission. So this means that the peak of thermal emission, i.e. the hotspot, has been shifted away from the from the substellar point. Or that it, in terms of a GCM output, in terms of a global map, on the right there, you can see a prediction for HD209 that would match up to that observation. And so the hotspot has been shifted something like 40 degrees to the east, and so the peak of thermal emission shifts in phase space of the phase curve. All right, let's get back to eclipse mapping. This is really what ultimately I want to do with all of this stuff is map. And so again, just a reminder, we're going to take ingress and egress, the way that the stellar limb occults the planet, recombine them, and we're going to get this lattice of information over the planet to try to reconstruct its thermal distribution. And so we've done that with these observations. We've taken these set of eclipses, these 7, 8, 9, 10 eclipses from each planet and each channel, and we have used the information there, all that structure in those residuals, excuse me, that structure in the ingress and egress, and we have used that to now fit the planet, not with a uniform model, but now we are going to fit it with a model that's derived from some non-uniform distribution. And for HD189 in both channel 1 and channel 2, here are some preliminary results. You can see that there is a different temperatures and different structures, different distributions, depending on which channel you're looking at. So we are now probing different levels of the atmosphere here, different pressures. We're at different points on that PT profile. And so we are really informing, we're informing those models now. And now we're starting to move into not just 2 dimensions, but 3 dimensions. At the bottom are some comparisons to some model outputs, and these are just kind of handpicked at this point, just for illustrative purposes. But you can see how, as you go, you can see how the different pressure levels create different shapes of the structure, and get a sense of what range of pressures that we're probing here. Similarly for HD209, I'm just going to show the exact same process, but I'm going to illustrate it just a slightly different way. Instead of showing the globes here, I'm going to show you the the GCM outputs in this map projection. So we use the information that we have from the eclipses to create this dayside thermal structure But we can also use the information from the eclipses to kind of connect what we think is happening on the night side. So what we want to see here is by using just eclipses alone, we of course are going to get those day side maps, but how well, by just understanding the day side, can we connect what's happening on the night side? So for HD209, here's our retrieved maps that are shown on the top panels. We can compare those to GCM predictions, again, to start to understand what pressure levels we're probing. And shown at the bottom are our retrieved phase curves. And we can compare those retrieved phase curves by using just eclipses to what we actually see by looking at the entire phase curve itself. So what I just popped up there is the Xelim HD209 channel 2 phase curve. And what I'm showing at the bottom in blue is our retrieved phase curve by using just eclipses. And you can see that we are in large agreement with the hotspot offset, and the phase curve amplitudes are all very similar. So we were able to get very similar information as the phase curve by just looking at secondary eclipses. Why is that interesting? Why does that matter that we can get all of this information from doing a secondary eclipse mapping rather than phase curves? Phase curves by default cost you in time whatever the period of the planet is. So a day and a half, 2 days, whatever it's going to be. Whereas a secondary eclipse is some very small fraction of that. Well, with Spitzer, you saw that we had to use 10 eclipses to build up the precision to start to make maps that had the resolution to distinguish between these pressure levels. With James Webb, that's not going to be the case. With an eclipse or 2 eclipses, 3 eclipses, you're going to be able to eclipse map just at definitely photometrically and probably at several different spectral bins as well. And so if you can get equivalent information at a cost of 12 hours or less versus looking at a full orbit phase curve as a function, at a cost of 24 to 30 something hours, it's going to be much more efficient to do secondary eclipse mapping rather than continue to do phase curves with an instrument like James Webb that is going to have such oversubscription issues. And so that is what we're hoping to show here, is not just show kind of the first 3-dimensional look at an exoplanet atmosphere, but to also establish some best practices for how to use the Webb instrument and how to efficiently use James Webb to get the same type of information going forward. All right, with that, I will take questions.
So maybe I wasn't listening closely enough. This is Jonathan Lenine. I thought you had said that the displacement of a bright spot in the infrared on one of these objects would result in a delay of a minute, but you had a delay of 2 minutes. Is that right, or is the timing correct?
Yeah, so it depended on the target. So for example, for HD209, what we saw was a delay of about 2 to 2.5 minutes. If I can get back to the right spot. So for HD209, for example, it's 2 to 2.5 minutes, right? And about 30 seconds of that we know we can explain by that travel time of the light across the system. So that knocks it down to 1.5 to 2 minutes. And then our predictions predicted something like a minute and a half. And so, to within that uncertainty of 30 seconds or so, those match up pretty well.
Okay, thanks.
Sean, the next question.
Yeah, thanks, Tom. Thanks, Brian, for the great talk. I had a question about star spots. So how would star spots affect your eclipse mapping measurements, and have they been taken into account in your current work?
Yeah, so that's a good question. Give me 1 second here. I'm going to stop this for a moment and then put it back up. Um, okay, so hopefully you're seeing a page here. So in the case of HD 209, it's very quiet, but in the case of HD 189, it is very much it is very active, and so we had this kind of contemporaneous ground monitoring of HD 189, and we were able to. So we did a study where we looked at the variability of HD 189 and measured, modeled out its variability and measured what its effect would have been on the eclipse depths and compared that to the uncertainty in our measurements. And so ultimately, the variability of 189 was still well within the uncertainty of our measurements. But yes, for active stars, that is, you definitely have to take that into account and make sure that you measure the star, monitor it and do that comparison.
Okay, thank you.
So I think, are you done, Nishant?
Yes.
Okay, so I think Ileana has a question, right? Ileana?
Maybe you're on mute.
Yes, sorry. I would like to ask this shift of the hotspots at different levels. Yeah, you show at different pressures. So I guess it's different levels in the atmosphere. So do you give explanations for that? If it's the circulation, if it's the thermal inertia?
Yeah, so this comes, so for example, what I'm showing at the bottom are the GCM predictions at those pressures. And so, yeah, that's just driven by the circulation. So you're looking at the comparison basically between like radiative and advective timescales at different pressure levels. As you know, so as you change pressure levels, your circulation is going to change, and your radiative process is going to change. And so you're just looking at how that manifests itself in this thermal distribution.
Okay, but you have also different composition in the atmosphere, I guess, so maybe it might be both things.
Sure. Yes. Yes.
Okay.
Yeah, and so I think that these models assume like equilibrium, assume a thermal equilibrium chemistry, and so they can look at the chemistry as a function of they reset that as a number of layers.
Okay.
I'm not the GCM modeler in the house, but that's my best understanding of how that is done. You can set these up in layers and then assume chemical equilibrium chemistry at each layer, and so run the chemistry and then run the apply that to your radiative processes.
Okay, thank you.
Anyone have more questions? Okay, so the Zoom meeting will be stay around until 1:30. So if you might have more questions, you could just go in and talk with Brian. And yeah, so let's thank our speaker one more time for the great talk.
Thank you.
Thanks, everybody.
Hello, Brian.
Yeah. Hey, Jayesh.
This is Jayesh. Thanks for the talk. It was great. I had one question about the timing. So you said about the difference of like 2.5 minutes, 2.5 minutes for the timing. So does this happen even in the consecutive orbits, like the consecutive orbits that have been measured? There, the difference of 2.5 minutes have been observed.
Yeah, that difference is